Similarly, we will now show the band diagram for the collector region, and in case of NPN transistor, again the collector is of N type with moderate doping. It means the Fermi level will shift above or towards the conduction band. Let us consider this is the shift in case of collector region, and this is my Fermi level in case of the collector region. Now we will discuss about the action or the working of the transistor with the help of these three band diagrams of the emitter region, base region and collector region, because these three regions are connected in case of transistor. Then we will move towards the energy band diagram of these three regions, and we will find out how these three regions will work connectively in case of transistor. In single energy band diagram, we have to align all these Fermi levels in a straight line. Let us consider this is my emitter region, which is I am representing here. This is my conduction band, this is my valence band, and this is my F1, that is Fermi level in case of emitter. Now in case of base, I have to align F1 with F2. If I will align F1 with F2, then I have to shift F2 in the upward direction, and due to this shifting, the valence band will move in upward direction with the same difference as the conduction band move in the upward direction. Hence, let us consider this is my Fermi level for the base region, and I have to shift the Fermi level of the base region in upward direction. Conduction band and valence band automatically will shift in the upward direction. Let us consider this is the shift of my conduction band. This is the conduction band in case of emitter, this is the conduction band in case of base, and let us consider this is the shift. Similarly, with the same magnitude, this will be the shift in the valence band of my base region. This is the conduction band of my base region, and this is the valence band of my base region. Now in the same diagram, I will show the collector's band. To align F3 with F2, I have to shift F3 in the downward direction, and if I shift F3 in the downward direction, conduction band of emitter collector region will also shift in the downward direction, and the valence band also shift. Hence, if this is the position of F3, then this will be the shifting of the conduction band. This is the conduction band of the collector region. Similarly, if the conduction band shift with this much distance, then the valence band also shift with this much distance. It means we now in this case there are three conduction band. This is the conduction band of emitter region, this is the conduction band of base region, this is the conduction band of collector region. Similarly, this is representing the valence band of the emitter region, this is the conduction band of the base region, and this is the conduction band of our collector region. In case of NPN transistor, emitter emit electrons. If it is having electrons in free state, it means these electrons are lying in the conduction band. Let us consider these are the electrons of the emitter, and these electrons are free. Now to move these electrons to the base region, we have to give some amount of energy to these electrons so that they can move from emitter to base region. And this energy is provided with the help of forward biasing. We have to forward bias the junction J1, that is emitter base junction, where this forward biasing of J1 junction provide sufficient amount of energy. These electrons will move from emitter region to base region. Let us consider out of 100 electrons, these all 100 electrons moves towards the base region. But we know that in base region the valence band is high as compared to the valence band of the emitter. Some of the electrons will recombine with these holes, and let us consider out of 100, 5 electrons recombine. It means 95 electrons will move from emitter region to base region. These electrons which are moving from emitter to base region without recombination, these produce a current, and this current is known as emitter current. This is our emitter current. Let us consider these 5 electrons which recombine with these holes. As we know that the J1 junction is forward biased, it means the p-type semiconductor, that is base, is connected with the positive terminal, and n-type semiconductor, that is emitter, is connected with the n-type negative terminal of our source. Then these 5 electrons which undergo recombination are produced here with the help of our forward biasing, and these 5 electrons will produce a current. That current is known as base current. As forward biasing is giving sufficient energy so that electrons from the emitter region moves towards the base region and gets sufficient amount of kinetic energy, they can easily move towards our collector region, because this diffusion or this length of diffusion is very small, as base region is very narrow. Electrons can easily move towards the collector region as the energy of the collector conduction band is small as compared to the conduction band of our base region. When these 95 electrons move in the conduction band of our collector region, they emit energy, and this energy is emitted in the form of heat. And due to this heat, the collector region temperature becomes high and it can damage our transistor. To make our transistor working in the safe mode, we increase the surface area of our collector region, so that if there is a large surface area, then heat can be easily moved in the surrounding. This is the reason why collector region is taken spacious, having large space as compared to our emitter region. Hence we find out that the electrons coming from emitter move to base, and some of the electrons from the base recombine with the holes in the valence band of the base, and left over the 95% of the electrons move in the collector region. And we get this, that the electrons or the emitter current is producing or divided into two currents, that is the base current and the collector current, where the base current is very small as compared to the collector current and emitter current. In some of our numerical problems, we take I base very small as compared to our collector current and emitter current. Hence, in many cases, we take emitter current is approximately equal to the collector current. The ratio of collector current to the emitter current is represented by that current gain, and in this case the current gain is represented by alpha. This is how a transistor works, and electrons move from electron to base terminal and base to collector terminal.